Welcome everybody. In this module, we will explore recurrent neural networks, often called RNNs. In the previous modules, we focused primarily on neural networks that process information in a single forward pass. Those models work very well when each input can be evaluated independently. However, many real-world problems involve sequences where the order of information matters. Examples include language, speech, financial data, and sensor readings that evolve over time. In this module, we will examine how recurrent neural networks were designed to address this challenge by introducing the concept of context and memory during processing. Our focus will not be on mathematical details or implementation. Instead, we will develop an intuitive understanding of how RNNs work, what kinds of problems they were designed to solve, and why newer architectures eventually began replacing them in many applications. By the end of this module, you should have a clear conceptual understanding of how machines can learn from sequences and why modeling time-dependent data requires specialized approaches. Before we talk about recurrent neural networks, we first need to understand why sequences matter in machine learning. Many real-world problems involve data that unfolds over time. In these situations, the order of information is not arbitrary. It carries meaning. For example, think about language. If we change the order of words in a sentence, the meaning can completely change. The sentence, "The dog chased the cat," means something very different from "The cat chased the dog." The same idea appears in many other domains. Financial data arrives as a time series, where yesterday's price influences today's interpretation. Speech signals are sequences of sounds that must be interpreted in the order they are spoken. Sensor data from machines or IoT devices also arise as streams of observations over time. In all of these situations, the data points are not independent. Instead, each observation is connected to what came before it. Traditional machine learning models often treat observation as separate and independent inputs. But when dealing with sequential data, this assumption breaks down. To correctly model these kinds of problems, we need algorithms that can understand order, track context, and incorporate information from earlier steps in the sequence. This is exactly the challenge that recurrent neural networks were designed to address. Now that we understand why sequence order matters, the next question becomes, how can a model actually remember what happened earlier in a sequence? This is where recurrent neural networks, or RNNs, introduce a very important idea: context through memory. Traditional feed-forward neural networks process inputs independently. Once the model produces an output, the computation is finished, and the network does not retain any information about previous inputs. Recurrent neural networks work differently. Instead of treating each input as completely separate, an RNN processes information step by step through a sequence. At each step, the model considers two things at the same time: the current input and the information it carried forward from the previous step. You can think of this as a running internal state inside the network. When the model reads the first item in a sequence, it forms an internal representation of that information. When the second item arrives, the network combines that new input with what it has already stored. This process continues as the sequence unfolds. In other words, the network is continuously updating its internal state using both new information and prior context. This mechanism allows the model to behave as if it has a short-term memory, helping it track patterns that develop over time. Because of this ability to incorporate prior context, recurrent neural networks became an important tool for problems where earlier events influence later outcomes. In the next slide, we will look at real-world problems where this type of sequential modeling has been especially useful. Now that we understand how recurrent neural networks incorporate context from earlier steps, let's look at where these models have historically been used in real-world applications. RNNs became especially valuable in domains where information arrives as a sequence and the order of events matters. One of the most important areas is natural language processing. Language is inherently sequential. Words appear one after another, and the meaning of a sentence often depends on what came before. Because of this, recurrent neural networks were widely used for tasks such as text generation, language modeling, and early machine translation systems. Another major application area is speech recognition. When a person speaks, audio signals unfold over time as a sequence of sound patterns. RNNs helped early speech recognition systems interpret these signals by analyzing how sounds evolve moment by moment. Recurrent models have also been applied to time series forecasting. Financial markets, energy demand, and economic indicators all generate data that changes continuously over time. By analyzing patterns across previous observations, RNNs were used to make predictions about future values. Finally, RNNs have been used in signal and sensor data analysis, such as monitoring industrial equipment, analyzing biological signals, or detecting anomalies in streaming data. In all of these examples, the key challenge is the same. The model must interpret information as it unfolds over time, not just as isolated observations. This is precisely the type of problem that recurrent neural networks were designed to address. However, despite these successes, RNNs also face important limitations, especially when sequences become long or complex. In the next slide, we will explore those limitations. Although recurrent neural networks were an important step forward for sequence modeling, researchers eventually discovered that these models also have significant limitations. One of the biggest challenges is learning what are called long-range dependencies. In many real-world sequences, information that appears early in the sequence may still be important much later. For example, in a long sentence, a word at the beginning might influence the meaning of a word near the end. Ideally, a model should be able to connect those distant pieces of information. However, in traditional recurrent neural networks, this becomes difficult. As the sequence grows longer, the influence of earlier information gradually fades as it moves through the network's repeated computations. In practical terms, this means the model may struggle to remember important details from the distant past of the sequence. Another limitation involves training complexity. Because RNNs process data one step at a time, training them can be slower compared to models that process all inputs simultaneously. In addition, the training process can sometimes become unstable when working with long sequences, making it harder for the network to learn meaningful patterns. These limitations do not mean that recurrent neural networks are useless. In fact, they played a major role in advancing sequence modeling. However, these challenges motivated researchers to explore new architectures designed to overcome these weaknesses. In the next slide, we will compare recurrent networks with feed-forward networks to better understand when each approach is appropriate. To better understand the role of recurrent neural networks, it helps to compare them with feed-forward neural networks, which we studied earlier. Feed-forward networks process information in a single forward pass. The input enters the network, moves through a series of layers, and produces an output. Once that prediction is made, the computation is complete. Each input is treated as independent from every other input. This approach works extremely well for many tasks. For example, feed-forward networks are commonly used in image classification, regression problems, and prediction tasks involving structured data. However, this structure has an important limitation. Feed-forward models do not maintain any form of memory. They cannot naturally track information that appeared earlier in a sequence. Recurrent neural networks address this limitation by processing information sequentially. Instead of treating inputs as isolated observations, RNNs maintain an internal state that carries information from one step of the sequence to the next. This means that when the model processes a new input, it does so while also considering the context of previous inputs. In simple terms, feed-forward networks are excellent for static prediction tasks, where each input can be evaluated independently. Recurrent networks, on the other hand, are designed for dynamic problems, where the order of information influences the outcome. Understanding this distinction helps us determine which type of model is appropriate for a given problem. In the final slide, we will look at why many modern AI systems began moving away from recurrent networks toward newer architectures designed specifically for sequence modeling. Although recurrent neural networks played an important role in the development of sequence modeling, the field of artificial intelligence continued to evolve as researchers search for more powerful and efficient approaches. Over time, several limitations of RNNs became increasingly apparent. One challenge is that recurrent networks process sequences one step at a time. Because each step depends on the previous one, many of the computations must occur sequentially. This makes training slower and limits how efficiently the model can use modern parallel computing hardware. Another challenge involves long-range dependencies. As we discussed earlier, information from earlier parts of a sequence can gradually fade as it passes through repeated computations. When sequences become very long, the model may struggle to connect distant pieces of information. Researchers also discovered that training recurrent models can sometimes become unstable or difficult to optimize, especially when dealing with complex data or very large data sets. Because of these limitations, new sequence modeling architectures were developed that could better capture long-range relationships and train more efficiently. These newer approaches introduced ideas such as parallel processing of sequences and more direct mechanisms for connecting distant parts of the input. As a result, many modern AI systems began moving away from traditional recurrent neural networks and toward architectures specifically designed to overcome these challenges. In the next module, we will begin exploring this next generation sequence model, which have become central to many of today's most advanced AI systems. Let's begin with cell 1 of the notebook. In this cell, the notebook prepares the computational environment so the rest of the workflow can run smoothly. The first thing the cell does is ensure that the required machine learning tools are available in the Colab environment. Because cloud notebooks sometimes start with a minimal set of installed packages, this step guarantees that the necessary dependencies are present before the analysis begins. After that, the cell imports the main libraries that will be used throughout the project. Some of these libraries are responsible for handling and manipulating tabular data. Others are used for visualizing information through graphs and plots. And another group provides machine learning utilities, such as splitting datasets, scaling numerical variables, and evaluating model performance. The cell also imports the deep learning framework that will later be used to construct and train the recurrent neural network. Toward the end of this cell, the notebook prints the version of Python and TensorFlow currently running in the environment. This is a useful practice in machine learning because it confirms that the system is configured correctly and helps ensure that the experiment can be reproduced later if needed. Immediately after that, the notebook continues within the same cell by importing the dataset. Because the notebook is designed to run inside Google Colab, the code activates a file upload tool that allows the dataset to be uploaded directly from the user's computer. Once the file is uploaded, the dataset is loaded into a structured data table so it can be explored and analyzed. Finally, the cell performs a quick verification step by printing a confirmation message, displaying the size of the dataset, and showing the first few rows of the data. This allows us to quickly confirm that the dataset loaded correctly and that the structure of the data looks as expected before moving forward with the rest of the analysis. Now, let's look at cell 3, where the notebook performs the first major stage of data cleaning and preparation. At the beginning of this cell, the notebook creates a working copy of the dataset. This is a common precaution in data analysis because it prevents accidental modification of the original dataset while we perform transformations and cleaning operations. Next, the notebook focuses on the date column, which is critical for a time series model like a recurrent neural network. The code converts the date information into a proper datetime format so that it can be interpreted correctly by the system. During this conversion, any values that cannot be interpreted as valid dates are automatically marked as invalid. Immediately after that, the notebook checks whether any rows contain invalid dates. If such rows exist, the notebook prints how many were found and removes them from the dataset. This ensures that the timeline of the data remains consistent and usable for sequence modeling. The next step removes exact duplicate rows from the dataset. Duplicate entries can distort patterns in the data and may negatively affect the training process. So the notebook removes them and reports how many duplicates were dropped. Once the dataset has been cleaned of invalid dates and duplicates, the notebook prepares the data for time series analysis by sorting the dataset according to store, product, and date. This step is essential because recurrent neural networks learn from sequences, so the data must be ordered chronologically for each store-product combination. After sorting the data, the notebook performs a quick missing data inspection. It calculates the fraction of missing values for each column and prints a small report showing where missing values may exist. This gives us a quick overview of potential data quality issues. If missing values are detected, the notebook applies a simple imputation strategy. Numerical variables are filled using their median values, which helps preserve the general distribution of the data while avoiding distortion from extreme values. For categorical variables, missing values are filled with the most common category in that column. These strategies allow the dataset to remain usable without discarding large amounts of data. Finally, the cell performs a few sanity checks to confirm that the dataset is structured correctly. It verifies that the revenue column exists, since that variable will serve as the prediction target for the model. And it prints a summary of the dataset's column types so we can confirm that the data is properly formatted. Immediately after that, the notebook moves into cell 4, where the focus shifts from cleaning the data to creating time-based features that will help the model learn patterns in the sequence. Again, the notebook begins by creating a fresh working copy of the dataset to ensure that transformations remain controlled and reproducible. The cell then extracts two basic calendar features from the date column, the year and the month. These variables allow the model to understand where each observation sits within the timeline. However, months have a special property. They are cyclical. December and January are actually close to each other in time, even though their numerical values are far apart. To represent this cyclical nature properly, the notebook encodes the month variable using sine and cosine transformations. This converts the month into a circular representation that better reflects the repeating seasonal structure of time. Next, the notebook prepares the target variable that the model will learn to predict. In many forecasting problems, revenue can vary widely and may contain extreme values. To make the learning process more stable, the notebook optionally applies a logarithmic transformation to the revenue variable. This transformation compresses large values and reduces variance, which can help neural networks learn more effectively. If the logarithmic transformation is enabled, the model will learn to predict this transformed version of revenue. Otherwise, it will simply use the original revenue values. At the end of the cell, the notebook displays a preview of the updated dataset so we can visually confirm that the new time features and target variable were created correctly before continuing to the next stage of the modeling pipeline. Now, let's move on to cell 5, where the notebook performs a quick exploratory data analysis to better understand the dataset before building the model. At the beginning of this cell, the notebook prints some basic descriptive information about the dataset. It shows the overall time span covered by the data, as well as how many unique stores and unique products appear in the dataset. These simple checks help us understand the scale of the problem and confirm that the dataset contains multiple store product time series rather than a single sequence. Next, the notebook examines the distribution of the prediction target, which in this case is the revenue variable that may have been log transformed earlier. To do this, the code generates a histogram that shows how frequently different revenue values appear in the dataset. Visualizing the target distribution is important because it helps us see whether the data is balanced, skewed, or contains extreme values that might influence how the model learns. After looking at the target distribution, the notebook explores the relationships between the numerical variables in the dataset. It calculates correlations among the numeric features and visualizes them using a heat map. This visualization allows us to quickly identify which variables tend to move together and which variables may have stronger relationships with a prediction target. Although neural networks do not rely directly on correlation in the same way traditional models do, this step still provides valuable intuition about the structure of the data. The notebook then shifts from aggregated analysis to examining an individual time series. It selects a sample store product pair and plots the revenue values across time. This visualization allows us to observe how revenue evolves over the months and helps reveal patterns such as seasonality, trends, or sudden changes in behavior. Finally, the cell explores temporal dependency in the data using a simple autocorrelation analysis. Autocorrelation measures how strongly current values in a time series are related to previous values. The notebook calculates autocorrelation for multiple time lags and displays the results in a bar chart. If strong correlations appear at certain lags, this indicates that past observations contain useful information for predicting future values. This final visualization is particularly important because it provides intuition for why sequence models like recurrent neural networks can be useful. If past values influence future outcomes, then models that can learn from sequences of past observations become especially valuable for forecasting problems like this one. Now let's move on to cell 6, where the notebook begins preparing the dataset specifically for the recurrent neural network by defining how sequences will be constructed. At the start of this cell, the notebook defines the look-back window, which determines how much historical information the model will use to make a prediction. In this case, the model will use the previous 12 months of data to predict the next month's revenue. This is a common approach in time series forecasting because it allows the model to capture seasonal patterns that may repeat each year. Next, the notebook defines the set of input features that will be used by the model. These include identifiers such as the store and product, contextual information such as region and category, and operational variables like price, promotional activity, marketing spending, holidays, stock availability, store traffic, and sales units. The time-based features created earlier, such as the cyclical representation of the month, are also included. You will also notice that past revenue can optionally be included as an input feature. Including historical revenue often helps forecasting models because it provides direct information about previous performance, although some practitioners exclude it if they want to avoid potential information leakage. After defining the features, the notebook specifies the target variable that the model will learn to predict. This target is the processed revenue value that was prepared earlier during the feature engineering stage. The notebook then creates a working dataset that contains only the relevant column and sorts the data again by store, product, and date. Maintaining this chronological ordering is essential because the sequences that feed the recurrent neural network must reflect the correct time order. Next, the notebook identifies which features are categorical and which are numerical. This distinction is important because these two types of variables require different pre-processing strategies before they can be used by the neural network. The cell then outlines a pre-processing pipeline that would normally handle these transformations automatically. However, because combining certain pre-processing tools with a deep learning framework can be complicated, the notebook instead prepares to perform the transformations manually in the following cell. That brings us to cell 7, where the actual feature transformations are applied. In this cell, the notebook begins by creating another working copy of the dataset that will hold the engineered features. It then converts the categorical variables into a numerical format using one-hot encoding. This process transforms each category into a set of binary indicators so that the neural network can interpret categorical information as numeric input. After the categorical variables are expanded into their one-hot representations, the notebook updates the list of input features to include these new columns. Next, the notebook standardizes the numerical variables. Standardization rescales numeric values so they share a common scale centered around 0. Neural networks typically learn more efficiently when numerical inputs are normalized in this way. Finally, this cell prints the total number of features that will be used by the model and displays a preview of the transformed dataset. This allows us to confirm that the encoding and scaling steps were applied correctly before the notebook proceeds to constructing the sequences that will be fed into the recurrent neural network. Now let's continue with cell 8, where the notebook performs one of the most important steps for a recurrent neural network, creating the sequences that the model will learn from. Up to this point, the dataset has been organized as a regular table, where each row represents a single observation at a specific time. However, recurrent neural networks do not learn from isolated rows of data. Instead, they learn from ordered sequences of observations. In this cell, the notebook transforms the dataset into those sequences. The process begins by grouping the data by store and product. This ensures that each time series is handled independently, meaning that the historical data for one store product pair is never mixed with another. Within each group, the data is sorted by date so that the observations follow the correct chronological order. Once the time series for a specific store and product is ordered, the notebook begins building sequences using a sliding window approach. Remember that earlier we defined a look-back period of 12 months. This means the model will look at 12 months of past data to predict what happens next. So for each store product time series, the notebook repeatedly takes a window of 12 consecutive months as the input sequence. The value that immediately follows that window becomes the prediction target. In other words, the model sees 12 months of historical information and learns to predict the revenue of the following month. Each of these sequences is stored in a list that represents the input data, and the corresponding next month revenue value is stored as the target output. After all store product combinations have been processed, the lists of sequences and targets are converted into numerical arrays that can be used by the neural network. At this point, the dataset has been transformed into the three-dimensional structure required by recurrent models: the number of samples, the number of time steps in each sequence, and the number of features describing each time step. The notebook then prints the shapes of these arrays, so we can confirm that the sequences were constructed correctly. Next, the notebook moves to cell 9, where the prepared sequences are divided into training, validation, and test data sets. The purpose of this step is to ensure that the model is trained on one portion of the data, while being evaluated on separate data that it has not seen before. First, a portion of the sequences is set aside as the test set. This test set will only be used at the very end to evaluate how well the trained model generalizes to unseen data. The remaining data is then split again into training and validation sets. The training set is used to actually train the neural network, while the validation set helps monitor the model during training and provides an early indication of whether the model is learning useful patterns or beginning to overfit. Finally, the notebook prints the size of the training, validation, and test sets so we can verify that the data was divided correctly. After the data preparation steps are complete, the notebook proceeds to cell 10, where the recurrent neural network itself is constructed. This cell begins by setting a fixed random seed so that the results are reproducible. The notebook then determines two key dimensions of the input data: the number of time steps in each sequence and the number of features describing each step. Using this information, the notebook defines the structure of the neural network. The model begins with an input layer designed to receive sequences of data. The first recurrent layer processes these sequences while preserving the temporal structure of the data, allowing the network to learn patterns that unfold over time. A dropout layer follows, which helps reduce overfitting by randomly ignoring a portion of the learned signals during training. A second recurrent layer then further processes the sequential information, gradually compressing the temporal patterns into a representation that captures the most important signals from the sequence. After the recurrent layers, the model transitions into fully connected layers that transform the learned representation into a final prediction. Because this is a forecasting problem, the model ultimately produces a single numeric value representing the predicted revenue. Finally, the model is compiled by specifying how it should learn. The notebook selects an optimization algorithm that adjusts the model's parameters during training, defines the loss function that measures prediction error, and includes an additional evaluation metric so that model performance can be monitored. At the end of the cell, the notebook prints a summary of the model architecture, so we can see the layers that were created and the number of parameters that will be learned during training. Now let's move to cell 11, where the model is actually trained, and then we'll continue into cell 12, where the notebook evaluates how well the trained model performs on unseen data. In cell 11, the first thing the notebook does is set up training safeguards, so the model does not waste time training longer than necessary or get stuck making tiny, unproductive updates. One safeguard is an early stopping rule. Conceptually, this tells the training process: if the model stops improving on the validation data for several rounds in a row, then stop training and keep the best performing version of the model. This matters because neural networks can start to overfit if they train too long, meaning they learn the training data too specifically and then perform worse on new data. The second safeguard is a learning rate adjustment rule. The idea here is, if the validation performance stops improving, the optimizer should take smaller steps so the model can fine-tune rather than overshoot. This helps training settle into a better solution instead of bouncing around. After these safeguards are defined, the notebook starts the training process. It trains the model using the training sequences and continuously checks performance using the validation sequences. It runs for up to a fixed maximum number of training cycles, but the safeguards can stop training earlier if improvement stalls. The batch size controls how many sequences are processed at a time during training, which affects both speed and stability. Once training finishes, the notebook visualizes what happened during training by plotting the learning curves. First, it plots the training loss and validation loss across epochs. This lets us see whether the model is learning steadily and whether overfitting starts to appear, because when training loss continues decreasing but validation loss rises, that is usually a warning sign. Then it plots the training and validation mean absolute error as a second view of performance. This is useful because mean absolute error is easier to interpret in terms of typical prediction error size, even if the model was optimized using a squared error loss. Next, the notebook moves to cell 12, where it evaluates the trained model on the test set, data the model has not seen during training or validation. The first step here is generating predictions for the test sequences. That produces the model's forecasted revenue values for those next month targets. Then the notebook includes a key step that depends on whether the revenue target was log transformed earlier. If the target was transformed, the notebook applies the inverse transformation, so the predictions and the true values are converted back into the original revenue scale. This is important because evaluation metrics like MAE and RMSE should be interpreted in the real-world units of revenue, not in the transformed scale. After converting back to the revenue scale, the notebook computes 3 performance metrics. One metric captures the average magnitude of prediction errors, another emphasizes larger mistakes more heavily, and a third summarizes how well the model explains variability in the outcomes. Together, these give a fuller picture of accuracy, rather than relying on a single number. Finally, the cell produces 2 visual diagnostics. First, it creates a predicted versus actual scatter plot. This plot is useful because if the model is performing well, the points should fall roughly along a diagonal line, meaning predictions closely match the true values. Second, it plots the distribution of prediction errors. This helps you see whether the model tends to systematically overpredict or underpredict, and whether the errors are mostly small with a few large misses or consistently wide. So in short, cell 11 trains the model carefully and shows how training progressed, and cell 12 evaluates the model on unseen data and visualizes how reliable the predictions are. Now let's look at cell 13, where the notebook demonstrates how the trained model can be used to generate a real forecast for the next month. In this cell, the notebook defines a small prediction function that takes a store identifier and a product identifier as inputs. The purpose of this function is to retrieve the historical data for that specific store-product combination and prepare it in the same format that the model was trained on. The function first filters the dataset so that only the observations belonging to the requested store and product remain. These observations are then sorted chronologically to ensure the sequence reflects the correct order in time. Next, the function checks whether there is enough historical data available. Remember that the model requires a fixed look-back window, in this case 12 months, to make a prediction. If the dataset does not contain at least that many observations, the function raises an error to indicate that a forecast cannot be generated for that series. If sufficient history exists, the function extracts the most recent look-back window of observations. These last 12 months of feature values become the input sequence that will be fed into the trained neural network. The sequence is then passed to the model to generate a prediction. Because the model was trained using the processed target variable, the prediction is converted back to the original revenue scale if a logarithmic transformation was applied earlier. The function then returns this predicted next month revenue value. After defining the prediction function, the notebook proceeds to automatically identify a valid store product series that contains enough historical data to produce a forecast. It does this by counting how many observations exist for each store product pair and selecting one that meets the minimum history requirement. If no such series exists, the notebook raises an error explaining that the dataset does not contain enough observations to generate a sequence of the required length. Once a valid store product pair is found, the notebook prints which store and product were selected, reports how many months of history are available for that series, and finally calls the prediction function to produce the forecast. The final output displayed in the notebook is the predicted revenue for the next month for that particular store product combination based on the most recent 12 months of historical data.